uh, how to integrate by substitution in this lesson, you see. But before we get into that, we would like to first have a hint as to when do we actually apply this technique of substitution to evaluate integral, because that's what matters most in integration, to realize or to recognize if you have to use substitution to tackle the problem or not. Because you can't just jump and try to substitute every time whenever you see an integral, but you just have to analyze if substitution is going to be a reliable technique in getting the problem done. You see. So now we're going to talk briefly as to what should you look for most of the time when you're dealing with a problem and you want to see if substitution is the best technique to try and do. You see. So here are the hints. So this is going to follow. This video is going to mostly assume the knowledge that we have actually covered in all the other areas. You see, that is, we have actually demonstrated how to integrate different types of functions, and we have shown you all the procedures and the recipes that you can use to integrate different types of functions. So now what we're going to do is we are going to work on the assumption that every function that has been defined, or which has a well-defined recipe for evaluating its integral, we are going to call such a function as integrable. You see that? And then a function which doesn't have any well-defined recipe on how to integrate it, we are going to refer to it as a non-integrable function. You see that? Because it is this issue of being integrable or non-integrability that we use to recognize if a problem can be tackled using substitution. You see. So substitution is used for integrals of the form. So the substitution technique, it is usually used quite often for integral of this form. You see that? So it's either you have an integral in which you have a product of two functions, f of x multiplying g of x dx, or at times you have a quotient, that is, you have f of x over gx dx. So these are two types of integral that you may encounter most of the time when it comes to integration. So when you come across an integral which has this structure, so most quite often such integrals can be tackled using the substitution technique. But in order for you to actually know whether substitution can work or not, you have to know how to do a background check for that. And how do we do a background check for that? You see that? So to see or observe or identify, to see or identify if an integral of the form above can be integrated by substitution, we check as follows. So if you are given an integral like the one that you have here, then there is a simple check that you can do. You see that? In order to identify that you have to use substitution or not. But what is it that you must do? So what you do most of the time is the proof or the check, it goes as follows. So what you do is you check if both the integral of f of x dx and integral of g of x dx can be found from simple rules that have been discussed. You see that? So one of the first things that you must do every time is that every time when you want to realize if a given product or a quotient will require the substitution technique to be implemented to evaluate it, then you have to check the two functions involved in a product individually. That is, you have to check that those functions, when you treat them separately, can you integrate them by the application of recipes that we have been discussing in our previous session. So if there is no recipe that has been designed to operate on such functions, we refer to such integral as not as not immediately integratable. You see that? So if no recipe for either integral of f of x dx or integral of g of x dx exists, then we say the function is not immediately integrable. You see that? So we say a function is not immediately integrable. So what you mean by that is that you cannot immediately integrate such a function. So any function which is not at the state of immediate integration, then that function, we can treat it as if it's not integrable at all. So this is are the things that you check out for if you want to see if the substitution method can work on that or it cannot be used. So as long as you can see that those two functions, there is one which is such that it is not at a state of immediate integratability, then we know for sure that substitution has to be applied. You see, so substitution is applied when there is a lack of immediate integrability. You see that? So whenever there is a lack of immediate integrability, we apply substitution. And that substitution is applied to that exact function which cannot be integrated immediately. You see that? So these are the things that you should know when it comes to the substitution technique, that it works on product questions, but it is always applied in those situations whereby you can pick one function for which there is no a recipe for immediate integration of that function. So every time when there is no written down recipe for the evaluation of the integral, then that function, we say it is not immediate integrable. So a function like that then needs fixing. So it is the fixing of that function where substitution comes in. You see that? So because every function which fails to be immediate integrable, it must be having certain things that are preventing us from doing so. So when we address those issues, that's where substitution comes in. So substitution is when we realize that here, if this was the case, things were going to be fine, is where it comes in. So it comes through that opening where we realize that if we fix here, everything will work perfectly fine. That's how substitution works most of the time. So now what we're going to do is we are going to start looking at examples so that we can actually get to understand what we mean by all this discussion that we've just laid down here. So to get a brief understanding, let's look at the first example as follows. So the first example that can be given, you can be asked to evaluate this integral. So you can be asked to evaluate the integral of maybe, let's say, x root of 2x squared minus 1 dx. So you can be asked to say, can you evaluate this integral? You see, evaluate this integral of x 2x squared minus 1 dx. So how do we deal with something like this? So to deal with an integral like this one, this is how we proceed. You see, so first you check these two functions. So these two functions, this one represents your function f of x, and this other one represents your function g of x. So what I'll do now is I'll consider these two integrals separate. So I'll consider the integral of x dx and an integral of 2x squared minus 1 to the power of half dx separately. So when you start analyzing these two integrals, there's one thing that you're going to realize, and what you're going to realize is that this integral, you cannot immediately integrate it. You see that? So we say it's not not immediate integrable. Why is it not immediate integrable? It's because there is no recipe for evaluating this thing in one step. But if what was inside was a linear, this was going to be an integrable function, because if you still recall what we did previously, we saw that there is a rule for evaluating an integral of this structure every time when the term that is inside the bracket is a linear. But since we have a quadratic, it means this thing, it has issues. So why do we have the issue? The issue because there is a quadratic term. So this x squared term is the thing that is causing problem. So the problematic area is the term that you always replace for. So we know that this integration was going to be integrable as long this thing was a linear. So which means what we do now is our starting point, we let that thing be a linear term. So what we do is we say let x squared be equal to u, where u now is going to take the position of x squared so that we have a linear term. But when x squared is replaced by u, the whole integral now must be written in terms of u. And to then find how to change the whole integral in terms of u, what you can do now is you can find the derivative of x with respect to u. You see, so what is the derivative of x with respect to u? So you know that when you differentiate x squared, you get 2x and then dx. Then when you differentiate du, you get 1 du, so you just get du. So which means we can see that x dx is du, and this implies also here that x dx is actually an equivalent of half du, like that. So which means now what we're going to do is everywhere where there is x, we're going to replace that x with the u's. So it means the u's now are taking over. So substitution is a technique of changing the variable of the integral. So every time when an integral is presented, it always comes with its own variables. Like x, whenever the integral says evaluate it with respect to x, it means the dominant variable there is x. So most of the time when you're doing substitution technique, substitution, it involves a transformation of an integral to be dependent on another new variable. You see, so it's a replacement of the original variable with a new one, such that now in terms of the new variable, the integration is very easy to do. So now we have actually find all this information. Now it's time to substitute it back there. So now if we substitute this information back there, what we get? So we get that the integral I is equal to what? So you see there is an x term that is sitting there. But already we know that from here, x squared is u, which means from here you can actually deduce what x can be by making x the subject. So look at the subject, you see that this becomes root of u. So which means now I'll have here x equals to root of u dot, then here we see x squared is replaced by u, so we get 2u minus 1, all this to the power of what? No, sorry. Yo, I made a mistake that was going to cost us a lot. There is no need to substitute that term together with the x term with that term, because if you look, our given integral can be written like this. So if you look, our given integral can be written as 2x squared minus 1 to the power half dot x dx. where I've taken this x and dx and I've grouped them together. Why am I grouping them together? Because these two guys, we can see them here. They are grouped like that, so they can come and replace that portion there, like that. So when we do that, what is it that we observe? So when we do that, what happens now is that we have I is equal to what? So whatever there is x squared, we put u, so we get 2u minus 1 all to the power of half. Then if you look at x dx, it is half du, so we get half du. And then now the next thing that happens is that this half, I can pull it out of the integral, so I have half integral of 2u minus 1 all to the power of half du. So if you look now, this is an integrable function. So what we have here now is an integrable function. Why is this an integrable function? Because you have a linear term raised to a power. So since now we have a linear term raised to a power, now we apply the recipe. So how does the recipe go if you still recall it? You know that first thing, you take the exponent of the, no, first you take the derivative of the term inside. So when you differentiate inside, you get 2, but you know that it comes out as a reciprocal, so you get a half coming out. And then the next thing is you take your term as it is, and then you increase the power by 1. So when you take half and you add 1, you get 3 over 2. Then you divide everything by the new power, which is 3 over 2. Then you add the integral constant. So the only thing that is left is just the simplification of these results. So when we simplify this, what do we get? So it's more like we have a quarter divided by 3 over 2, which is more like just saying a quarter dot 2/3 dot 2u minus 1 and 3 over 2 plus k. But now this simplifies nicely. So therefore, what is I? So the integral I now is going to be, if you take 2 there, you get 1 over 6. Then u, remember, is standing in the position of x squared. So we get 2x squared minus 1 to the power 3 over 2, then plus k. So this finishes the integral. So this is how you make use of integration by substitution to solve problem. But it will be good also if we can try also another different example other than what we have just seen here. So let's try another different example to keep more practicing. So another example, it goes as follows. You see that? So evaluate the integral of cos x e2 sin x dx. So we want to evaluate that integral. So how do we go about the evaluation of such an integral? So for the evaluation of such an integral, this is how we proceed. So first we check, we analyze these two separate integrals. So first I look at the integral of cos x dx, and then I look at the integral of e2 sin x dx. So if you look closely, you will see that this guy here, this one, is immediate integrable, because you can immediately integrate that. So we say this thing is immediate integrable. But when you analyze this one, on the other hand, the situation is different. So for this guy, it's not immediate integrable. And so from the fact that this guy is not immediate integrable, that's where our substitution is going to come in. So what is the problem with this guy? We see that the exponent can only be immediate integrable when the power is a linear term, but now we have a function sitting there. So what we're going to do is we're going to remove that trig function and replace it with a linear term. So this is how we proceed. So we're going to say let u be equal to sine x. So when you differentiate both sides, you will see that du is actually, when you differentiate sine x, you get cos x, then dx. Easy, like that. Now, what is our integral I? So if you look at our integral I, it can be written as integral of e2 sine x bracket cos x dx. We can write our integral like that. So when we write our integral like that, we can see now that definitely sin x can now be replaced with that. We get e to u. Then cos x dx, if you look closely, you will see that this guy cos x dx is here, so it's going to replace that guy there. And therefore, if we do that, what happens? So if we do that, what we just get is du. Now we're just integrating it, eu. But what is the integral of eu? So you know that the integral of eu is just eu plus k. So therefore, it means the integral, final integral I is e to u, but u is sin x, so it's going to be e to sin x plus k, like that. So this is how you perform integrals using substitution. It's all about looking at the two functions involved, either in a quotient or in a product, and then see who can replace who. You see, who can replace who. So let's look at another one more last example. So another example that you can try, let's try maybe something like this. So they say evaluate the integral the integral of cos x over sin x dx. So they will say evaluate this kind of integral. So now how can we deal with an integral like this one? How can we deal with an integral like this one? So to deal with an integral like this one, this is how we proceed. So at first, we look at the integral separately. So we can check that because this function can be written as so if you look closely, you will realize that this guy that we have here, this integral, it can actually be realized as the integral of cos x times 1 over sin x dx. So which means now we have this guy being our f of x function, and then this guy being our g of x function. So this is what we have. So we look at those two separate integrals. So we look at first the integral of cos x dx, and also we check the integral of 1 over sin x dx. So if we recall from the rules, there is no rule for this integral. So this integral that we have here is not integrable, this one. You see? So it's not integrable because there is no immediate rule for evaluating that. But this one, there is an immediate rule for it. But what could be the problem here? The problem is that we have a trigonometric function in the denominator. And we know that any integral of the form 1 over something can only be immediate integrable when what is at the bottom is linear. So that's our substitution point. So what we do now is say let u be equal to sin x. So this implies what is du? So it means du becomes cos x dx, like that. Then now, what is our integral? So now, if you look closely, you will see that our integral that is given, it can be written as the integral of 1 over sin x times the integral of cos x dx, like that. So which means we can see now that this guy that we have here is actually the same guy that we have there. So we can replace it there. And then because of that, it means now what we get. So it's going to be the integral of 1 over sin x, but sin x is u, so we get 1 over u. Then cos x, that is du. Now this is integral of 1 over u. So you know the logic, you differentiate, you get 1, so you get 1. So your final answer is going to be ln of u, then plus k. And what we get then afterwards, we get ln of u. What was u? We said u is sin x, so you get sin of x, then plus k, like that. So this is one thing that you should know, that every time when you're dealing with these integrals, this is how you evaluate them. Simple like that. So this is how the substitution technique works. This is how the substitution technique works most of the time. It's a matter of checking if both your functions are integrable according to the rules that you've been given. But if it cannot be integrated immediately from the rules, then it means it needs fixing, like that. You see. So one more example, which can be the last one, is evaluate. So we want this. So we want to evaluate, let's say, t e to t squared dt. So you're given that integral, and then they say, can you evaluate that integral? So how can one deal with such an integral? So to deal with such an integral, again, we look at them individually. But remember, this checking thing, you must never write it in an exam. You just do it in your head. It's just that I'm putting it explicitly, but naturally you do it in your head. You see. So we see that we have these guys. So if you look at these guys closely, you will see that this one here is fine. You can immediately integrate that. But when you pay attention to this one here now, things here not make sure. So this is not integrable. And why do we say this is not integrable? There is a quadratic term here. So what we need is, we usually need a linear term here. So our rules allow us to do stuff when we have a linear term there. But since we do not have a linear term there, there's nothing that we can do. So therefore, what we simply do is this. So we have those two guys, and we have seen that this one is issue. So what we do is say we let u, but it's not u that you can use. You can use m is equals to t squared. So what does it imply? It implies dm is equals to 2t dt, like that. So we can see from here, it follows that half of dm is equal to t dt. So now, what do we see? So we can see that our integral I can be written as e to t squared, then t dt. So which means, according to what we have, is going to be the integral of e to t squared, which is e to m. Then we can see that t dt is half of dm, so it's not half of dm. So you see that you can pull out the half outside, and when you pull out the half outside, you're left with em dm, which is just going to be em plus k, which is then going to be half of e to t squared plus k. So that finishes off. So yeah, this is how you use the substitution technique to evaluate integrals. So every time when you want to evaluate integral using the substitution technique, this is how you go about it.